Good afternoon, everyone. As Ollie's said, my name's I-Hsien Porter, and I work for JBA Consulting, where for the past 15 years, I have been working with hydraulic models of river flooding. But this project is slightly different because earlier this year, one of my colleagues approached me and asked, would I get involved in the Grand Union Canal Transfer scheme? It's a water resources scheme that will transfer recycled water from the Midlands to the southeast of England. It's not a new project, it's been running a few years, but we were entering a new phase of the study. They needed another hydraulic modeler involved. And so I said yes, it sounded interesting. And I was also quite intrigued as to whether I could take the skills that I've learned from flood risk modeling and apply those to a very similar type of modeling, but in a very different context. Could we do that, and could we push the software in those directions? So this is a presentation that's about the scheme. It's about how we're using Flood Modeler on one component of that scheme. I'll talk about the model that we built and how we model the transfer. But it's also my personal take on moving from using Flood Modeler for flooding to Flood Modeler for a slightly different purpose. And as Ollie said, I last gave this presentation at the Flood Modeler conference a couple of months ago. But since then, I've added to it, so I will do my best to stay within time. Apologies if I go slightly over. But since then, I've added 3 unanswered questions. And these are loosely based around some of the Q&A and the discussion that we had at the conference around this talk. And the questions that I've started thinking about a lot more as a result of this project. And so I'll explain a bit more about those when we get there. I think there's a few people registered from overseas who have joined this talk. Looking down the list that I got sent beforehand, visitors from Australia, Germany, Ghana, India, you're all very welcome. Here in the UK, this year we've experienced a very dry year, and many regions of the country are still in drought. I'm sure we're not alone. But that's led water companies to seek alternative sources of supply and also measures to reduce demand. And that's all had wider impacts on the wider environment, economy, and society. So it's quite timely that earlier this year, the Environment Agency, which are the government agency responsible for water resources in England, the Environment Agency released the National Framework for Water Resources. This is an update of a report that was last released 5 years ago, but in this year's report, it comes up with this headline figure that by 2050, we will need an extra 5,000 megalitres per day of water to meet all sources of demand across England. So that's 5,000 million litres of water per day, in addition to what we currently use. That's kind of difficult to visualise, so that's equivalent to 4.5 Wembley stadiums or 2,000 Olympic swimming pools per day, whatever works for you. What the schematic on the right there shows is that, of course, these demands are not evenly distributed around the country. So, for example, in the southeast, which is where I grew up, that region on its own accounts for over 2,000 megalitres of that demand, over 40% from the southeast alone. And the water industry is responding to this. It's responding in several different ways with new reservoirs, new water transfer schemes, desalination schemes, and so on. And so the Grand Union Canal is one of a number of options that are intended to improve the resilience of water supply, but in this case, specifically targeting that demand in the southeast of England. So this is what the transfer route looks like. The scheme actually involves 3 canals, the Coventry Canal, the Oxford Canal, and the Grand Union Canal. And collectively, these are England's longest canal network, linking the Midlands with London. And this map shows the transfer routes represented by our Flood Modeler model. It's about 135 kilometres long. There's just over 4,000 nodes in this model. So when I opened Flood Modeler and saw this view for the first time, I realised I'd let myself in for something slightly more complex than I first thought. But in terms of what will happen, the idea is that water will get treated at Minworth Advanced Water Treatment Works, which is just outside Birmingham in the top left of the map here. It will then be pumped through a pipeline to the canal, where it will discharge into the canal at Atherstone. And then it will flow south through the canal before being abstracted again somewhere just south of Milton Keynes, where it will be pumped again through a pipeline, treated and stored in a covered reservoir near Luton. So that's the transfer route. It's a joint scheme between Severn Trent Water, which is the water company where the water originates, Affinity Water, which is the water company on the receiving end, and also the Canal and River Trust, who manage the canal. And when it's complete, the whole scheme aims to transfer up to 115 megalitres per day. That's the maximum transfer that we'd expect under drought conditions. Much of the time, the volumes transferred will be somewhat smaller, but up to 115 megalitres per day is what we're aiming for. Again, to give that something a bit more visual, that's around 2 swimming pools an hour, if that works for you. Now, with a scheme like this, as you can imagine, there are many different contractors and consultants involved, of which JBA, my employers, are one. And there's a few different ways that we're involved. So at a very large scale, we need to understand how the transfer flows will interact with the day-to-day operation of the canal and the network of reservoirs that the Canal and River Trust use to manage water levels in the canal. So we're involved in water resources modelling. And that image there is just a screenshot from Aquator, which is the software we use to do that. Zooming right in at the other end of the scale, we're also doing some very detailed computational fluid dynamics modelling of individual structures. And that lets us look at the detail of velocities and flow rates and how they vary in the channel, and the impact of some of that for things like navigation of the canal by boats. And then somewhere in between those scales is the work that I'm directly involved in, which is our 1D hydraulic model, which allows us to look at how all the different components of the canal are linked together, how they interact with each other over the long distance of the transfer route. And that's what I'll talk about for the rest of this time. I'll say a bit more about how we built that model and then how we went about modelling the transfer through it. So this table on the left gives an idea of the scale and complexity of the model. And as you can imagine, it's built up of a range of different data sources, cross-section survey, LiDAR, topo survey, and so on. Something we did that was quite interesting, though, was that a few select bridges along the route, we had some 3D laser scans of those structures, and that's what the image on the right there shows. And these allowed us to build up a very detailed picture of those bridges. And the reason that was important was that a lot of these structures are quite old. They date from the 19th century in some cases. And so over time, subsidence, general ground movement has led to deformation of those structures. And so it was important for us to be able to understand the detailed picture of those bridges so that we could understand the most restrictive point for navigation by boats. And that became important for some of our analysis later on. Now, of course, when you think about canals, you think about lock gates, because that's how levels on canals are primarily controlled. And there's quite a lot of one of these structures, actually. So I'll spend a little bit of time just explaining how we modeled these in our model. So you can see in the schematic on the right there, I'm assuming you're broadly familiar with Flood Modeler, but in the schematic on the right, we've got a couple of sluice gates that represent our locks there. Of course, in reality, what happens when a boat uses these locks is the lock gates open and close. The boat moves through, but some flow of water also moves through with it. And the problem is this flow of water through the canal depends entirely on the boats using the canal. And that's not something we can easily represent in a nice, neat set of criteria in our hydraulic model. And so what we do instead is that the Canal and River Trust, they monitor lock usage. A lot of these lock gates are telemetered. And that gets published as an annual report. But from that, they were able to calculate for us a time series of the lockage flows, the flows through those locks. And this is an example of one of those time series just on the screen there. So this is for a 3-month period. And as you can see, the lockage flow fluctuates as there are peaks and troughs in the usage of those lock gates by boats. Worth noticing the y-axis, though. These are some pretty small numbers that we're dealing with. For someone like me that's used to flood modelling flows of 0.05 cubex, meters cubed per second, these are very much on the small end. But this is the sort of flow rates that we're dealing with on canals, and that becomes important a bit later on. That time series, that was supplied to us, and that gets represented in the model as an abstraction unit that allows flows between the upstream and downstream of the lock gates. Now, locks also have something called by-weirs. There's an example highlighted in this picture here. And these allow the canal levels to be balanced again by allowing water to bypass the lock gates. So, for example, if there's too much water in one of the pounds, perhaps the next set of lock gates upstream has let more water in, there's another source of flow. The by-weirs allow water to bypass the locks and allow the levels in the canal to become balanced again. And so that gets represented in our model as a spill unit or sometimes a culvert, depending on the nature of the structure. And then last but not least, some locks also have a back pump. So this allows us to rebalance water levels the other way if it's necessary to pump water from a lower up to a higher level again. And so that gets represented in our model as an abstraction unit with a set of logical rules. So there's quite a lot to one of these structures. And of course, this gets replicated many times throughout the model. And what all of these structures are trying to do is to regulate the regulate the water level within what's known as a normal operating zone. So this is a water level that's contained within the banks of the canal with plenty of freeboard. It's high enough so that boats can navigate the canal without running aground, but it's not so high that the boats float so high in the water that they have difficulty with navigating bridges and tunnels. And so when it came to calibrating and proving our model, the test that we did was to run the model with a number of different flow scenarios and to look at whether the structures in the model were able to regulate water levels back to the normal operating zone as they would in reality. And this is what we found. So this is two separate flow scenarios from two very different periods of time, a very wet and a very dry period. We derived inflows to the canal network from these periods of time, and then we compared the modelled water levels to the normal operating zone. And initially there were some differences, and that prompted us to look again at some of the model schematization. We commissioned some new survey to be more confident in some of the by-weir heights. We calibrated Manning's end values. But in the final model, which is what you see here, the water levels are within about 50 millimeters of the normal operating zone in most cases. And for our purposes, that was satisfactory. So in summary, at this point, we've built up our model from a range of different survey sources. The key structures that we needed to get right are the lock gates, and there's more complexity to those than it might first appear. But then we were able to build confidence in that model representation by comparing modelled water levels to the normal operating zone and looking at whether the model was able to regulate those levels back to the normal operating zone as they would in reality. So that brings me to the first one of my unanswered questions that I mentioned. Because how do we know that our model is replicating those water levels in the canal for the right reasons? So in other words, how do we avoid problems with equifinality? Now, this is not a new question. It will be very familiar to many of you. But in summary, one of flood modelers' strengths, I think, is that it's modular. And what I mean by that is that you can take a structure, a complex structure like a lock gate, you can break it down into its constituent parts, and you can represent each of those parts with a different unit within the software. But of course, each of those units has its own coefficients, and in a model like this, we can end up with a model that's very heavily parameterized. And very often the observed data we have is just too sparse to answer the question of which parameter set is right. So that's not a new question, as I say. What is new, or perhaps newer, is ways that we can now answer or think about answers to this question. So I mentioned earlier that we're doing some detailed computational fluid dynamics modeling in some areas of individual structures. And with those models, by explicitly modeling more of the processes that are involved, they can provide us with predictions of flow or velocity that we can then use to calibrate our 1D models, or at least give confidence to the choice of parameters or coefficients that we're using. Now, as far as this project's concerned, that's something that's maybe in the future. It's not something we've looked at yet. But I think we do need to get comfortable with the idea of working with multiple models that each tell us something new about the system. So seeing ourselves not just as model builders, but as scientists answering a question with those tools that we have at our disposal. So that's the model we've built. We then needed to convey the transfer flow along the network and somehow represent that. Of course, if we're wanting to transfer a flow along the canal, we require a hydraulic gradient. We need that hydraulic gradient in order to generate a flow rate. And the problem is that in the very long pounds, this potentially raises water levels at the upstream end to the extent where it could exceed the bank heights, and then that water would be lost from the system, and then that's wasted water. And so we know in some areas, the banks are going to need to be raised to contain that extra water that we're adding into the canal. And the modelling allows us to predict where those areas are. So these are draft maps, but they show the areas that are most likely to be affected. So this is now the model with the transfer flows added in. The red and the orange colours, they highlight where the differences between the water levels and the normal operating zone are much larger. Up to ½ a metre in some cases. So it's great that the model allows us to predict this. We can look at the areas most likely to be affected or needing bank raising work. But it still potentially means there is quite a lot of time and expense in this scheme involved with raising the canal banks along long stretches of the canal. So what the modelling's also allowed us to do is to try some different options that might mitigate some of that. And so one idea that we've been looking at is the idea of building some new locks to effectively make these very long pounds shorter. So the idea is that you'll build a new set of lock gates roughly midway along the pound. Within each of the newly created sub-pounds, the hydraulic gradient would therefore be less likely to require bank raising. But then, of course, you would need a pumping station to allow the transfer flows to be pumped around the lock gates when they're closed. So that's a theory. What it might look like is something like this. So again, these are draft results, but this shows an example of a pound with and without a transfer lock. And in this case, we're predicting that it will lower water levels by around 200 millimetres. So that sounds promising. What that means for bank raising, I can't really answer because that assessment needs to be completed by the engineering consultants. And there's a lot of other factors beyond modelling that influence that decision about where and by how much to raise the banks. But what I think we can say is that the transfer locks will have potentially quite significant benefits in terms of the time, the cost, and the footprint, the construction footprint that they'll occupy compared to some potentially quite widespread bank raising. So in conclusion, at this stage, we've run our model with some transfer flows, and we know that in order to generate a flow rate, we need a hydraulic gradient. Some bank raising is going to be needed to contain those highest transfer flows, but we've been able to use the modelling to explore some different ideas using some additional locks, for example, to reduce the amount of bank raising that will be needed. Now, there's something quite interesting here because through this project, we're dealing with some quite small numbers. So that 200 millimetre drop in water level, okay, that's visible. But some of the flow rates I mentioned before, they're very small. If you remember that time series of lockage flows, 0.05 QMEX. And so that brings me to the second one of my unanswered questions, which is what computational tolerances are appropriate when we're applying flood modeler to water resource problems, where we're typically looking at much lower flow rates. I had a really fascinating conversation with Conrad Adams about this at the conference. But assuming that you're familiar with Flood Modeler, then you'll likely be aware of some of the advanced computational parameters, HTOL and QTOL. So this is a level and flow tolerance. If the solution is within these tolerances at a given time step, the model is said to have converged. Now, if you're not sure what that meant or what these parameters do, then there is an excellent webinar by Matthew Valois at Jacobs that I think is still available on Jacobs' website, and I'd refer you to that. The point that I wanted to make is that in this study, we are trying to detect quite small changes in flow or water level sometimes. And what's more, the simulations we were doing lasted 3 months. And that was because we wanted to understand the sort of seasonal variation in lockage flows over time, like I showed before. So over that time period, even if we only tolerate a small error at every time step, that error could potentially accumulate. So does that mean that we should be tightening our convergence criteria? The values I'm showing on screen, they're the default values, but what makes these particular values acceptable for a flood study? And what values would be appropriate for a water resource study? And how would we assess that? And I don't think we understand that enough yet, but by doing this work on the Grand Union Canal, these questions that we haven't really considered before are now becoming a lot more relevant. In the last part of this presentation, I'll cover something slightly different. So I mentioned earlier that the transfer flows may need pumping stations to be passed around some of the additional locks, that idea that we were thinking of before. But of course, that's true of all the existing lock gates. Most of the time, the lock gates are closed, and so the transfer flows are going to need to be bypassed around them. And that requires either gravity bypasses, like the bi-weirs, or some form of pumping stations. And those pumps are represented in the model in various different ways, such as those that I've showed on screen. But I'm not going to go into detail about how these are modeled, because instead, I mentioned earlier that I was coming to this project partway through. And so this model had already mostly been built at the time that I joined. And I'm sure others have had this experience, but it's far harder to make sense of a model that someone else has built compared to when you have been through that process of building the model yourself. So I now needed to make sense of all these pumping rules and different units in what is a relatively complex model. And so I did what a lot of people do nowadays, which is I asked ChatGPT to help me out. Now, you're welcome to scoff at my very amateurish approach to using AI and ChatGPT. I'm not an AI expert, but I am sharing this as a hydraulic modeler, confronted with a problem, just trying to make use of some tools at my disposal to make sense of that. And what I figured was that flood modeler files, they're plain text files, and so I could upload those to ChatGPT. I use ChatGPT, other AI systems are available, but I upload those to the AI, and I could get the AI to give me a nice, neat summary of all of those model rules, and it would present things in nice, easily digestible formats that would save me having to go through the model meticulously, unit by unit. So to begin with, I asked ChatGPT to do something straightforward, counting the number of river sections in the model. That's something I could very easily check afterwards. So I did give it a bit more than just this prompt. I explained the background to what I was doing and the structure of certain things and what I was aiming to get out of the file. And it thought for a bit, and it came back and it told me, there are 34 river sections in your model. Now, I happen to know there's over 3,000 river sections in the model, so I was pretty disappointed, actually, by what the AI was capable of. AI does get some things wrong. But then I figured, well, ChatGPT hasn't been routinely trained on flood modeler models, so it needed me to explain the structure of the file in more detail. And of course, this is what a river section looks like in a flood modeler geometry file when you look at it in a text editor. And so I explained the general layouts, the different keywords where it could find different pieces of information. And it thought for a little bit longer, but it came back and told me there are over 3,000 river sections in your file. And I happen to know that that's correct. So I thought I'd take things one step further. And so I asked ChatGPT to list all of the abstraction units in the model and identify which of those had logical rules associated with them. Now, when I first started at JBA as a new graduate, straight out of university, my line manager at the time, he wouldn't let me use the user interface of Flood Modeler. I had to do all of my model edits in a text editor. But as painful as that was at the time, it was actually a really good way to understand the structure of the files and how they interact, how the software interacts with them. And so I can very quickly recognize that this is an abstraction unit called Hawkesbury P. It's got a set of logical rules associated with it, and there are the rules listed underneath. And so what I then started doing was training the AI in the same way that I'd been trained all those years ago to recognize the different keywords in the file, how they relate to each other, and where it could find different pieces of information. And this went on for a while. I'm not sure how long it took. I maybe lost track of time. But eventually, the AI was able to generate a summary of all the logical rules associated with abstractions in the model. And this was something that I could perhaps start to use in a more ready format. Now, this process is repeatable because ChatGPT records what it's doing as Python code, and that code can be used independently or with the Flood Modeler API. What I was effectively doing was writing that code by describing what I wanted in plain English. And so if you already know how to code, maybe AI doesn't offer that much more, although it might get you there a bit quicker. If you don't know how to code, if it's unfamiliar to you, then it's possibly a gateway into a little more automation. And that brings me to the last one of my unanswered questions that I started thinking about as a result of this project, which is, what skills do flood modelers actually need for this AI age? Now at JBA, I'm a team leader. This is my team. I also deliver training courses, and so it is part of my responsibility to train people to use modeling. But if we can get AI to do things, well, what skills should we actually be teaching these people? Now, I personally don't believe that people are about to be replaced by AI systems. And the reason that I believe that is that I don't think there will be widespread public acceptance for decisions to be made by AI algorithms where those decisions concern fundamentally important things like flood risk or water supply. And there is evidence for that. We're already seeing things like the Keep It Real movement in the US, where some companies are making a virtue out of not using AI in their products or advertisements. Admittedly more in the performing arts sector, but the concept is established. So I think there is still an essential role for people in gaining trust and acceptance, determining the types of models we use, how we use them, making decisions on that information. And that's why I think webinars like this are actually quite important, because it's our opportunity to share how we're using modeling and to learn from what other people are doing as well. So what I've talked through this lunchtime is the Grand Union Canal Transfer scheme. We've built quite a complex model of that scheme, but we've been able to use that model to start exploring ideas that will potentially influence and guide some of the design decisions that are made later on in that scheme. And lastly, I've used a little bit of AI to try to make my life a little bit easier. And I have mixed feelings about it, actually. It has potential, but it does get some things wrong, and you do need to be very descriptive in what you're asking it to do. So I think for now, at least, we still need flood modelers, the people, to make the most of Flood Modeler, the software.